Everyone. So I would like to begin with thanking the organizers for putting together this wonderful conference and for giving me this opportunity to speak. Today I would like to tell you a story about fermionic dynamical phases with measurements in terms of its topological classification and adaptive circuit realizations. So the main theme that the talk is about is topology in general. We know very well by now it's a general principle for understanding quantum phases of matter, especially in equilibrium. And we classify the bulk states according to its topology, and then the topology also helps you protect certain degrees of freedom that may carry energy or conserve charges or both on the boundary, right? The most classic example, probably you would hopefully agree with me, that it's the Chern insulator or Landau level, whichever one you prefer. And then you could study, the Chern number in the bulk, and then you know that there's some chiral mode running on the edges. You could study it on the lattice model with full translation symmetry. You could study in a totally disordered or amorphous system. The same phenomenon goes. That's how robust the idea of topology is. And over the years, there has been a lot of development in understanding topology in equilibrium. One of the things that I would like to highlight is this table, which I'm going to use at a later point. But this table is, I think, considered to be one of the big success in thinking about topology. In particular, this is about topology of fermionic system with time reversal symmetry and particle symmetry. And it's kind of amazing that if you just have these two ingredients, even without any interaction, so long as you think about fermion band structure, you have this giant table. First, you start here. There are 10 different combinations of time reversal symmetry and particle symmetry. It's called the tenfold way. For each symmetry class, it's a specific combination. You go to a specific dimension, you look up this table, and this table immediately tells you how many different classes there are, right? So it's a pretty amazing and systematic result. You don't need any interaction. And of course, interaction will give you more, but this is some very interesting things to start with, even without interactions. Okay, but ultimately, this is all about equilibrium system that has been under a lot of scrutiny. And if you think about it, equilibrium system by definition is a system that has, even though it doesn't care about it doesn't care about spatial translation symmetry, but equilibrium system always have continuous time translation symmetry. And you have the notion of energy that helps you define the notion of energy gap. And all these are basically falling under the category of gap system. Okay? So what if we want to go out of this constraint? We can definitely break the time translation symmetry by making it not continuous. For example, if you think about a 4K system with a drive frequency omega, then your time translation symmetry becomes discrete. Well, yet in this case, you can still talk about energy, but just modulo the drive frequency. You can still talk about band structure, a related notion, and define topology accordingly, right? But in this type of system, there is sort of a difficulty that you may run into, because if you want to talk about these are strictly unitary, and if you started to have the time periodicity compromised, then you may worry about heating the system to infinite temperature and you lose the topology and all that. So these are question mark, whether or not you can save it by localizing the phase in some way. Well, that's, I think, still under investigation. And this talk will be about a system that has no symmetry whatsoever in terms of space-time symmetry, no time translation symmetry, no spatial translation symmetry whatsoever. And the type of system that I want to think about is dynamical systems. Well, in particular for me, I want to do fermions, because for reasons that you will see very quickly, with measurements. And when I say measurements, I wanted to at least record a measurement outcome. If you just record a measurement outcome and don't do anything, people usually call that the monitor system. But if you want to make use of the recorded outcome and do something later according to the measurement outcome, then it falls under the name of adaptive circuit. So I want to include both. So I want to just say, at least you record the measurements. And so just for cartoon, you should imagine a bunch of fermions on a lattice, and then it evolves under both unitary operations and measurements. That's the type of system we want to think about, okay? But of course, I'm going to not go fully classify all of these according to the topology or anything, but I want to restrict myself to talk about something that is the analog of a gap insulating phase, which we want to talk about in equilibrium. And the dynamical analog of that is the so-called area law phase, which is pretty dominant by measurements. You have a lot of measurement going on, so you don't have a lot of entanglement developed across space. And then this is the type of phase we want to focus on. Just like in equilibrium, we back in the days of Landau, you would think, you know, the not an order phase, a boring insulator is just one phase. There's only one phase out there, but later people realized that they can be distinguished according to topology, and you will see the same kind of phenomena appearing in here in fermionic systems. Okay, so this is our goal. Okay, this is a quick outline of my talk. I will tell you about the classification of free fermion area law topological dynamics. So I'm going to restrict myself to talking about free fermion, because even with free fermion, you can already get a lot of amazing results. And of course, we wouldn't stop here in the end, but this is a good point to start. And then I will tell you about a notion which I find fascinating called dynamical bulk boundary correspondence, which you will see at a later point. And then this correspondence will help us understand how, in general, I would like to, can we construct dynamical models that would exhibit the topology that I classify over here. And these are the main reference of the talk, which are done in collaboration with my wonderful collaborators. Assad is my student at Cornell. Haining Pan is currently a postdoc at Rutgers, and Hassan is currently at Zifra. Okay, so let's start with something rather concrete to give you an idea, you know, what type of system we're talking about more concretely, and why can we do topological classification of these systems. So I want to talk about what does it mean to talk about, what does it mean to have free fermion dynamics with measurements. Just imagine I start with something concrete, a chain of Majorana modes, and then you have some circuit that generates dynamics. Every one of these circuit elements, it could be a unitary gate or it could be a measurement. When it comes to unitary, I want to think about a type of unitary that is just exponentiated fermion bilinears. So by any metric, you would agree that this is sort of a free fermion evolution. For measurements, you can also think about those measurements that are free. For example, if you just measure the joint parity of neighboring Majoranas, let's say weakly, then depending on the measurement outcome, the wave function collapses in different ways, but the wave function collapse is basically captured by this such type of non-unitary evolution, which is still exponentiated fermion bilinears, right? And this lambda parameter is the measurement strength. If you crank it up to infinity, that's the good old projective measurement that we are familiar with. Okay, so in any case, with all these circuit elements, you can imagine that the evolution of the problem is free because the entire evolution is exponentiated from bilinears. And if you have an incoming state that is Gaussian, free, or Slater determinant, whichever terminology you like, these are basically synonyms, then the system would stay that way, right, throughout the evolution, which is nice for theoretical handle editors. Okay, of course, this is sort of a many-body description of a free problem. There should be just a single particle description of the problem, which is helpful to think about. And indeed, you can extract a single particle description of this entire circuit by thinking about the Heisenberg picture. That means you think about how the single fermion operator, these Majorana modes, how they evolve in time upon the conjugation of this evolution operator. It could be this, it could be that, it could be the product of both. The key feature here is that single fermion operator always evolve into single fermion operators at a later time. That means all you have to keep track of is how they get linearly mixed with each other. And we call this matrix that handles the linear mixing, the transfer matrix. Okay? Right. This transfer matrix is particularly helpful because it has all the information that you want to remember for the circuit. As it turns out, if you carefully think about this transfer matrix, you can kind of map it to a completely unrelated sounding problem, which is a problem, you know, if you start with a gate, V, you describe it using a transfer matrix, and on this side, you should think about just a single particle scattering problem around a potential. Imagine the potential is just here, and you have some incoming plane wave, indicated by red, and some outgoing plane wave indicated by green, right? So if you think about the elastic scattering problem, ultimately, when you solve the quantum mechanics, you end up with some linear relation between the amplitude between these modes, right? That linear relation can be encoded using an S matrix if you're trying to relate the in state with the out state. However, if you just say, I want to label the linear relation between these guys at one y coordinate with, you know, different y coordinate, then you use the idea called transfer matrix. As it turns out that through the transfer matrix, you could establish the sort of equivalence between these type of problems. Why do I do that? Because if you now think about all of these gates stacked together forming a circuit, which is basically the picture that you saw on the previous page, on this side you have a bunch of scattering problems stacked together form a total, like a connected scattering network. And this type of setting is something that occurred before. It's called a Chalker-Connaughton scattering network model, and it's just one way to formulate the famous Anderson localization problem. Over here, you have space and time. Over here, every direction is space, right? You don't have time here because we're just talking about elastic scattering that talks about scattering at a fixed energy. So time doesn't matter for this problem. Okay? And then on this side, if you're thinking about the space-time propagation of, say, a single fermion operator, on this side, you're basically, equating this with the spatial tunneling amplitude of a mode being sent in here and, let's say, pick up at another spot. And in the circuit problem, you always encounter randomness because when you measure, oftentimes you cannot have 100% definitive outcome. You have some random outcome coming out here, and it naturally maps to disorder pattern in this circuit model. So there's a natural correspondence between these two models, but if you're super careful, you may tell me that, hey, these are not exactly the same because measurement outcome follow this very interesting thing called Born rule, whilst disorder, if you're an experimentalist, you may say it's just how the materials are baked in the oven, or if you're a theorist, then it's whatever you said in the beginning for your model. It's not going to change according to the physical state. So this change of probability distribution could lead to change in the phase diagram comparing these two models, but for the type of phases I'm going to talk about, it's most likely not going to do anything, so I'm going to take that as an assumption. Forget about the difference between the probability distribution. And, well, like I said, I want to focus on area law dynamical phases in, let's say, n+1 spatial dimensions. Through the mapping that I showed you in the previous slides, it gets mapped to disorder localized phases in the n+1 spatial dimension, all right? It's space-time and space here. Okay? What are these? Well, this is the stuff. The big table that I showed you on the first slide was classifying. If you say you have either time versal or particle hole or both, you go into one of these 10 classes, and then you pick your favorite dimension, and you have a lot of things to look at. Every one of them has already been classified. And essentially, through the mapping I showed you in previous page, every one of these entry has a dual version in this world. So there's some interesting dynamical phases to talk about. So this is sort of a high-level classification, and then basically the remaining question is, what do these entries really mean in this world? Right? So this is what I'm going to hopefully show you. All right, and then in fact, if you are very familiar with these type of problems, some of these dynamical problems are secretly also due to problems in error corrections. So some of these entries in here has a lot of interesting implication to be unpacked when you think about them as dynamical problems via the duality. And if you're careful, you notice that I put an asterisk here for symmetry because the notion of symmetry in here, of course, is natural. It's a symmetry for a localized phase, right? But from a scattering network problem, usually you could think about symmetry in this way. If you have a symmetric problem under whatever symmetry you prefer, you have some in-state that are symmetric. Via the symmetric scattering, the outstate should carry that symmetry. However, you see that the in-state and outstate are arranged in this funny way, so reading it as the symmetry of the circuit needs some reformulation. All right, I will leave it at that for a moment, and then we'll come back to this. But don't take the symmetry as the literal symmetry of the circuit. Okay, this is a lot of things to unpack. Let's look at something rather concrete. Just Majorana chain with dynamics in 1+1D. Cannot be simpler than that. And then if you go look at this classification, you should focus on this so-called symmetry class D, which does have particle symmetry, which is natural because we're already working with Majorana, no charge conservation. But secretly, there is an extra time versal symmetry. I can explain where this is coming from, because actually the dual localized phase is characterizing both the evolution of the bra state of the dynamical side and the ket state of the dynamical side. So there's sort of a time versal symmetry between bra and ket. That's how extra symmetry could emerge on this side. But nevertheless, if you understand all of the mathematical detail, which I don't want to bother you with, you should look at this box. 2-dimension, class D. So you find 2 classes, all right? 2 different classes. These are the 2 classes of time versal invariant topological superconductors. On the dynamic side, it's actually really easy to understand why there are two classes, because you can have two types of measurement dominant phases. You can have all the measurements completely localizing on the even bond, or the measurements completely localizing on the odd bonds. It will favor two types of Majorana dimerization pattern, and we know from study equilibrium system that these type of dimerization patterns, they're fundamentally distinct. So these two pictures are really sort of dual to each other, which is very easy to understand. And what I'm going to basically tell you, basically from here, you know that you cannot go from this picture to that picture without causing a phase transition. And in fact, these phase transition have already been studied in various contexts and different models already previously. But here I want to just emphasize that these two are topologically distinct. Okay, so this hopefully give you some confidence that this big table is not just some high-level math. There's some concrete realization of the story. And in fact, there's some fun game that you can play, because if you know how to build a circuit to realize each dynamical phase, why don't I build a circuit with domain walls and ask what's living on a domain wall? Because from equilibrium physics, we know that there's always some funny stuff living on a domain wall between two topological phases. And from the picture I showed you probably you can guess that there should be some Majorana mode dangling living in here, which you can actually see. This is a real numerical simulation on a chain of 128 Majorana modes. These two regions are basically where I parameterize the circuit to put the two different phases. You see domain walls. They're not really sharp. There's a profile, but not quite visible. And I initially entangled this whole system with some reference system just to keep track of entropy. And there's this interesting notion, which is not general, but works for free fermionic. It can tell you the spatial distribution of entanglement between the physical system that I keep track of and the reference system. You see that once the evolution starts, most of the places become white. That means when the physical system is being measured, it quickly gets disentangled from the reference system. However, there are some dots here that really hovers around the domain wall. These basically means that the domain wall modes still remain entangled always with the reference system until they meet each other, right? When they meet each other, the domain wall modes are still there, but they can be measured together and get disentangled from the reference, so you don't see it anymore. Okay, so it's really like this topology is still protecting something, not energy, not charge. It's entanglement in this story. Okay, and then you can play with some trijunction geometry to break these domain walls to generate entanglement as well, which we show in this paper. All right, if you're interested, you can go check it out. So essentially, what I show you is this picture. Right? For a Majorana chain, the space-time 1 plus 1D is dual to some class D3 topological superconductor into spatial dimension. But if you only look at the boundary, you see this dimerization pattern. But if you want to use the technology of classification, then it's class D, just superconductor by itself, and then in 1D, it's P-wave superconductor. In fact, this picture is one special example of this general idea that we would like to propose. You can have this very general idea called dynamical bulk boundary correspondence. That means if you have a dynamics, areal dynamics, the entire dynamical process, if it has some topology, it also gets manifested by the steady state ensemble that you see when the system sort of saturates in the long time limit. Okay, we have quite this is one model. We have other 1D models that exactly match on this picture. And in fact, there are even also high-level argument that tells us that this has to be, this should be correct. For example, like I said, the bulk via the mapping that I showed you, you can always dualize it to Anderson localization problem. Hence, you can go classify the dual localized phase according to this table. But if you just look at the final state ensemble, these are basically states of fermions that are also free area law. So they should fit somewhere in here, right? So apparently, I would have two different ways to classify the whole picture. But the interesting thing is if you go from the bulk to the boundary, you shift the dimension by 1 this way. And like I said earlier, you need to reformulate the symmetry carefully. And as it turns out that the result is that you shift the symmetry class upward by 1 click. These tables are usually organized in such a way that if you move the dimension this way, move the symmetry this way, the classification stays entirely the same. It basically means that you can go classify the bulk dynamics directly. You can look at the final state. It's just the same thing, right? And then the 1D, the 1 plus 1D model exactly match onto this very general picture. So this dynamical bulk boundary correspondence also kind of give us a general recipe to construct the other states that are difficult to kind of imagine in general dimension. Because now if you do want a quantum circuit model to realize these topological dynamics, you have a simple design principle. You just try to find a quantum circuit that can target certain topology in your final state ensemble. And you can even try to do better. Let's just say I want something better than a final state ensemble that could still be random. I want one state that show up in the end, all right? Which you can actually do without doing any interaction or anything. All you have to do is that, well, cook up a quantum circuit that not only have measurement, but also feed-forward procedure that depends on the earlier measurement outcome. And with this, you can actually hit the ideal ensemble that only contains one single state. And you can tell me whichever one state you like to have, and I will tell you how to create such a adaptive protocol to hit the desired state. All right? So, for example, if you want to go here, which means you want a circuit that targets Chern insulator, of course, the classification is Z, as we know very well. And then, you know, I'm going to basically quickly show you how to hit the states, right? And I want to just quickly mention that this is different from any sort of finite time preparation of Chern insulator, because I'm curious about the entire dynamics, which is supposed to run forever. So if you want to put it in the context of state preparation, it's not only just preparation, it's also a stabilization algorithm that help you stabilize this phase indefinitely. And in fact, if you can, it's also again some kind of a phase that is robust against noise. Okay, I guess I'm running a bit short on time. I will keep it quick. So actually, I just need one slide to tell you how to do it. Normally, you think about state, for example, the Chern insulator state using some band structure. There are some bands that you want unfilled. I call them minus bands. Some bands you want filled. I call them plus bands. Instead of thinking about momentum space, I want a real space picture for these states. And these n's plus are basically some number operator living in these bands. These are number operators in these bands. I want them to be spatially localized. Had I not have any Chern number, I would just create the Wannier orbitals and just use the occupation basis for the Wannier orbitals. You can see that, you know, these are basically the desired occupation you want. But if you have Chern number, there's Wannier obstruction, not a big deal. You just go for some localized over complete basis, which can circumvent the Wannier obstruction caused by topology. And if you want something more concrete, think about the Gaussian-looking coherent state in your lowest Landau level. That cannot be more localized than that, right? But yeah, you just do over complete basis. And the adaptive protocol kind of follow the idea of the so-called always-on error correction. This is how you would do it. Go measure one of these things one by one, okay? And if you see a match with this, it means that the state locally is already what you want. So move on to the next guy. If you see a mismatch, it means that you're either missing a particle or you have an excess particle. Then try to exchange charge with the bath to get rid of that error. And that's it. You locally fix the error right away. And since these n operator does not necessarily commute with each other, so you don't want to stop after one round, you just have to keep going, and then these will converge very quickly. And these are operations that are local up to exponential tails. Okay? I'm going to show you quick numerics that says it converges very quickly. So here it goes. This is I would like to say that all of the description that I described on the previous slides are still non-erecting. All the measurement, all the feed-forward operation, they're still Gaussian non-erecting, so you could simulate these very quickly, even on a classical computer. But that's just to prove that our adaptive circuit will work. The other thing I want to say is that all of these n operators, they have exponential tail. So I guess it depends on what kind of background you have. If you are more condensed matter background, you may say exponential tail is no big deal, it's still finite range. But if you're a more circuit person, maybe you say, well, you don't want to see exponential tail. If you want a local circuit, it has to be strictly local. So yeah, you can do that, but just cut out the tail. Do a finite range truncation of these operators. You will have a finite range circuit. These tails are there to ensure that you can hit this state every time exactly. If you truncate out the tails, the state that you end up in a long time limit will basically still be psi dressed by some small amount of disorder. But the key thing is if you don't truncate too violently, the topology stays exactly the same. All right? So the state will have a little bit of variation over runs, over time, but the topology is going to be the same. This is a specific numerical simulation that we have. We choose this fortunate or unfortunate choice of -1 Chern number for my target space, target state. Nevertheless, when we run this finite range circuit, the Chern number converges very exponentially quickly over the circuit time to the desired value. And this Chern number is calculated using some real space version of the Chern number that we find in this Kitaev's paper. Okay, so and I think if you believe that this is really the representative of a phase, it should have some robustness. And also, I call it kind of a always-on error corrections. From that perspective, you should also ask if there is any robustness. So we also try to test the robustness of our protocol, and we use this kind of a noise model, which is basically a random phase that depends on the random rotation of phase depending on the local density of a site. You do it for every site, every round, with phi, a random variable that is within this range. And of course, this sigma, which is the range, is basically a parameter for the strength of the noise. All right. Of course, when sigma is 0, there's no noise. And you see that the Chern number is robust when you crank up sigma till a certain point where it starts to deviate. And maybe you don't see so exactly where is the transition point, but if you use some other entanglement metric, for example, mutual formation between, say, two strip on the system, you see nice crossing behavior, which is usually an indicator of some phase transition that happens. This is an entanglement phase transition, right? So basically, this is sort of the quote-unquote noise threshold of the error correcting, the always-on error correction algorithm, if you like to think of it that way. Or you could say that this is the point where you trigger phase transition away from the area law phase. That is the topological phase that I initially wanted to build a model for. Okay, there are other things that you can look at. For example, now, you know, topology is supposed to protect something, right? So let's try to look at domain walls. You could have, let's say this is already only space. You can have programmed the circuit so that in these domains, spatial domains, you target Chern number 0, insulator, boring insulator. In this area, you go for the Chern -1. So at the domain wall, you just kind of interpolate them however you want. It doesn't matter so much. And then you try to run this circuit and see how things behave. As circuit time goes, you know, you can use this thing called local Chern marker to ask whether or not the Chernness within around a certain point is, if it is agreeing with what you want. So you quickly see that there's some randomness going on here, but it quickly goes to this blue and white situation. Blue means Chern number is -1 locally at every single point here, and is 0 in outside regions. This happens in order 1 time. And again, if you look at the entanglement contour, anywhere in the so-called bulk of the domain, it becomes white quickly. That means, you know, the purification dynamics happen very fast. The measurement quickly killed off all the entanglements there is initially built in between the physical system and any reference system you begin with. But you see that, like, there are traces on the boundary that are left. And in fact, these dynamics on the edge are pretty slow compared to what's happening in the bulk. Okay, so this is still a sort of an evolving story. We are still trying to find a better way to quantify what exactly is happening on the bulk. But for sure, this tells you that there's some slow dynamics, some sign of edge modes in this completely out of equilibrium sort of system. There are actually more. You can try to interpolate from one topological phase to another. Of course, we expect the topological phase transition. Yeah, indeed, we see signs of topological phase transition. phase transition. And then with this adaptive circuit, you can ask this question that has been asked, I guess, multiple times today already. You could follow each single quantum trajectory and ask for its behavior, or you can just ask what is the average behavior across all the trajectories. And for experts, this is asking the question about the difference or potential convergence between the entanglement phase transition and the so-called absorbing phase transition. And these is the traces for turn numbers for a single model, and then they look very different. And you know, this guy has a rather sharp jump, but this guy that is, this is the average behavior. This is the behavior of every single trajectory independently examined. You see that they look very different. They have very different transition point and behavior. Okay, so this is a quick summary of what I told you today. I gave you a classification of free fermion area law dynamical phases, starting from symmetry classification, and then every class for area law phases, the landscape gets subdivided according to their topology. And then I also gave you a picture of this dynamical bulk boundary correspondence that relates the topology that is hidden in a dynamical process in the space-time bulk with the steady-state ensemble that is effectively sitting on the temporal boundary of the space-time. And then using this, I show you how to construct general models for these interesting topological area law dynamics using the idea of always-on error correction. Right. With that, I will thank you for your attention.
Thanks a lot for the great talk. Questions? I think Sun Won.
Hi, thank you. Maybe you explain this, like how do you impose specific target symmetry on your circuit, and then can you impose the target symmetry without post-selection?
That's a very good question. So there are classes which you can almost get for free. For example, class D3. Again, this symmetry class is talking about a dual Anderson localization problem. D3 is just vanilla circuit on Majorana fermions. That's all you have. The most generic thing you can do on a lattice of Majorana fermions is in class D3. If you want charge, if you put in charge conservation, you automatically go to A3. But you did ask a very interesting question, and indeed we have some results in this later paper that says certain symmetry classes, if you want to keep the system free and non-interacting, you do have to post-select. But if you don't care about whether or not the system is free or not, then you could hit every single class, no problem. For example, the classes that would lead to issues is classes that comes with, after the reformulation, comes with time reversal doublets. You don't want to say you have a time reversal symmetry that preserve a Kramer's doublet. Your measurement are not supposed to resolve which one of the states within this doublet, because that would, wave function collapse one way or another would break the time reversal symmetry there. You don't want that to happen. And if you enforce that, in some of the trajectories, it will look as if you're enforcing sort of a Gauss-Weyler projection that causes interaction.
To make sure, then most of your numerical simulations are 2 plus 1D.
Most of there are 1 plus 1D
1 plus
models
1D,
and also 2 plus 1D
So
models.
those are free numerics, and that means you impose a post-selection for the numerics?
No, well, post-selection, I don't do any post-selection. Every time I say when a measurement is about to happen, I calculate the Born rule probability mechanically. We just calculate the Born rule probability, do a coin toss according to that probability, evolve forward. So I do respect the Born rule. And then if there are adapted protocol in the circuit models, then I'm just gonna do things according to, later unitaries could depend on the earlier coin toss results. Yeah, that's how the simulation is done. So no post-selection. But indeed, I'm following individual quantum trajectories. Yes.
Okay. More question here?
Yes, thanks for the great talk. I just want to clarify, is the statement that any dynamics that stabilize the corresponding phase will have this noise robustness, or is is it property of the particular construction that you're studying, or is it property of the phase? Just to.
I believe they should all have stabilities because ultimately it's the same idea like topological phase of matter. You can analyze it at a point. It's supposed to cover a finite range of phase space. It's robust. The topology itself is robust. I cannot guarantee that every time you hit the same state with noise, but say in here, you know, the topology, like the Chern number states -1 till some point that you hit, at which you hit a phase transition.
And can I ask maybe a quick second question? Like, what happens to free bosons? Like, can you do the?
Right, that's an interesting question. Mechanically, the mapping doesn't quite work that way. For bosons, you also have to deal with this infinite Hilbert space, which is also kind of tricky. Measurement also does, yeah, quite dramatic things. So yeah, short answer is I don't exactly know what happened to free bosons.
Next question, please.
Can I ask a question? So, if I understand correctly, in your vanilla first example about D3 class D3 in 1D, the domain was has a trapped Majorana mode that seems to suggest that there's some information is retained in this dynamics. Is that always the case in your topological state on the domain, or say, for example, in your Chern insulator example, does that boundary mode also related?
Yeah, that's a very good question. That's the part of the evolving story. All I can tell you here is that we see traces of these this modes, and then it has slow dynamics. In a way, you could say that the 1+1D example with the single Majorana mode, it has infinitely slow dynamics in terms of entanglement. It never gets compromised, never goes away. All you have is just this Majorana mode jumping left and right. This is more complex because it has sort of one spatial dimension. I don't have a full characterization of this dynamic mode for you ready, but at least we see signs that they exist, and their dynamics is much slower than what's happening in the bulk.
Okay, thanks. So just a quick question. I actually don't quite understand what is this plotting in this.
Oh, this game?
What is entanglement contour?
Right, so, okay, let me, so this went a bit quick. Let's start with the situation where the physical system is entangled with some reference. Okay. The entanglement contour calculates the spatial distribution between the entanglement, of the entanglement between the physical system and the reference. It's still a thing specific to free fermion system. Normally, talking about distribution of entanglement is not quite sound.
So you just mean the mutual information conditioned on your measurement record, is that correct?
More than that, because you have to take into account that for free fermion, the interesting thing, or maybe the less interesting thing, is that entanglements are happening mode by mode. So this entanglement contour basically tells you that which modes are actually entangled with the reference system. So it's it's really a spatial distribution, and it's a helpful metric for us to locate these boundary modes.
Okay, got you.
Not that I think interaction will immediately destroy these, but I will lose this tool to see them.
Not just fluctuation of the occupation of the mode, because if you consider mode by mode, the only thing you can do is occupy or not. It's all entanglement is all
for a single particle, yes. For free fermion system, that's indeed true.
This is basically fluctuations of the mode.
You could say that, yeah. Yeah, that's right.
Okay. Next question, please.
Yeah, thanks for the very nice talk. Can the transitions between the area law states be also realized as some Anderson transitions in the corresponding?
Loosely, yes, but this is where the difference between the probability distribution come in. The change of the distribution, the difference between Born rule and some whatever disorder configuration, probability distribution, does change the universality class of the localized, quote-unquote, localization transit. I mean, Anderson localization is Anderson localization, but if you try to naively bring that to the world of circuit, then the probability distribution does change the universality class.
So what can be like a physical consequence of this difference? Like how can I see the difference?
For example, we do have a study, well, maybe the reference is not on the slides, but we do study the difference between the two. In fact, in this context, in this sort of context where we try to interpolate between this and this, and you could compare the literal Anderson localization problem, that is the transition between these two, and you could study the circuit problem. We see different critical exponents. Yeah. And sometimes the phase, well, this is one example, but sometimes the phase diagram could change in even more dramatic way that I'm happy to share, but it gets complicated.
Okay, thanks.
Thanks for the very nice talk. So I have kind of like a broad question. I can understand from your talk that if I already have some non-interacting periodic table or interacting one, I can use your algorithm to kind of like generate the wave function for such systems.
Yes.
So are there like some unique topological phases that only exist in this kind of a circuit system, like adaptive circuit system, like beyond the tables for closed system topological insulators?
That is a very good question. The short answer is I actually don't know.
Okay.
So I think previously, okay, we have to go pretty far. In this type of system, with 4K system, people do realize that there's something that goes kind of beyond, you know, just equilibrium topology. But those structure does rely on having a temporal periodicity. And yeah, it's a very good question. Whether or not I can have something that is so esoteric that is, you know, with measurement that has no relation with equilibrium topological phases, I don't know. But I wanted to say at least the bulk boundary correspondence that I propose here sound like a interesting principle, which should be tested more, but it definitely kind of works for non-interacting system. And in that picture, you always, you know, looking at the topology at the sort of the final time slice is kind of a way to probe the bulk topology. So by that, yeah, so you can always see some sort of almost equilibrium type topology here.
Yeah, also a quick question, like technically, how do you handle the spatial boundary? Because you are preparing wave functions, and I suppose that you probably should take some periodic boundary conditions, for otherwise the bulk wave function edge ones are not the same. If you really take open boundary conditions, how do you handle the wave function on like close to the boundary part?
Close to the boundary part? You mean technically?
Yeah, like for your numerical simulation or the technical constructions, because for instance, if I have a non-interacting system, for instance, I have a chain insulator wave function. In the bulk, I can just do a block wave function. It's eigenstate for with a quasi-momentum k.
Yeah.
But if you really take an open boundary condition, the wave function in the boundary is different. There are some edge modes.
Right. So essentially, I did not do that exactly, but this case is essentially already that. I'm sorry, you have to fast forward for that. This case is already like that. You may ask what exactly is the thing I do right at the boundary. To be honest, it doesn't matter. We try different protocol. It's some version of it is just literal truncation of these modes that I measure. So I literally use the truncated mode.
You just cut the circuit.
Literally cut that. That's fine. Or some other ways of interpolating them doesn't really change the picture at all.
I see.
So I think that effectively answered your question.
Okay, thanks.
Okay. Yes.
I have maybe a very naive question. So based on my understanding, when using Chern number to do this classification, Chern number is an integer, right?
Correct.
So my question is, how should I understand that you do have a kind of continuous change of the Chern number value during this dynamics? How should I think about the nature of the phase in the intermediate region?
You are asking about this
yeah,
curve?
This one, yes.
That's a good question. Initial state is not area law or anything. So initial state is a mess, right? Okay. And then you get zero Chern number. As you evolve in time, the system gradually purify, gradually start to look more and more like an area law state. But if you just stop here, I can't really say what it is. It's a non-equilibrium state that is not area law. So you know that for the Chern number to be quantized, we have to at least talk about some phase with a short range correlation. Right? So if you just go here, there's still some remaining long range correlation.
Okay, thank you.
Not saturated. Yeah.
One last brief question.
Yeah, just to clarify about the noise robustness.
Yeah.
Do you need like a strong symmetry or something in general? Like if you have like, you don't need the noise to respect the symmetry? Because I mean, like,
no, the noise is this, so it's just some random phase rotation. So it does preserve.
Right, but I mean, this example was class A. Or
A3.
Something? A3. Okay. So
well,
it did have a symmetry then. I was
wait,
curious,
sorry. Okay.
I mean, it's even. I'm just confused because then it's like even better than equilibrium.
Oh,
you don't even
I think
the symmetry.
I think I need to clarify something. Yeah. There are two different ways to talk about the same setting. It's an adaptive circuit. If you do follow every single quantum trajectory, it's a closed system, okay, including the bath. You know, I could just put the bath inside as my part of the system. You could just do something so that the bath does nothing but creating some local disorder, whatever, but it doesn't do anything. However, if you do want to trace out the bath and think about the average dynamics, that means you convert this into a quantum channel story and only look at the physical system, that's the point where you lose the strong U1 symmetry, if you care about that.
Okay.
So, but yeah, they're just...
But even in the disordered case, you require disorder that respects a symmetry.
Oh yeah, the noise is just some random phase notation, random phase depending on local density.
Okay.
Yeah. So it will try to mess up the local mode wave function, essentially. That means my stabilizing condition will get messed up because these n get messed up because of the random phases. That's a way to sabotage this adaptive protocol. And of course, if you do it too much, then you lose the topology in the final state.
Thanks.
Okay. Thanks very much again for a great talk.
Okay.